Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about a fundamental phenomenon in probability that has very important implications for statistics and data science. That phenomenon is the law of large numbers. The law of large numbers states that when we average a large number of independent random variables that have the same mean and finite variance, then their average is going to converge, in a certain sense that we will explain, to the mean of the distribution. This justifies using the sample mean or average of samples from the random variables to estimate that mean. In a way, we have come full circle, because if you remember, when we defined the mean of a random variable, we defined it so that in a way it would represent the average of samples from the distribution of the corresponding random variable. So it's nice to have finally a mathematical justification that if you actually do that, under these independence assumptions, you are going to get a good estimator of the mean. In statistics, the implications are that if you want to estimate a population mean from random samples, as long as you take enough random samples, eventually you're going to get an arbitrarily good estimator of the population mean. Let's get to it. We're going to talk about the law of large numbers and also about the mathematical tool that is used to establish it, which are deviation inequalities, which are in general a very important tool in probability theory. Our motivation is the estimation of population parameters. So remember that the logic here is that we want to estimate a parameter that describes a whole population which is too large for us to measure each individual. For example, we want to estimate the weight of the rats, the average weight of the rats in New York. We cannot catch all the rats, but we can catch a subset of them. And that's exactly what we do. We catch a random subset chosen uniformly at random from the population and also independently at random. This is an example where we're trying to estimate the mean height in a population. This is the histogram of all the samples, but what we actually get to see is this smaller number of samples. And we hope that computing the sample mean here will approximate the population mean. This is the estimate for this particular set of samples. If we repeat the sampling process, we're going to get a different estimate. And yet again, a different estimate. So we have to analyze our estimator probabilistically. This is the distribution of the estimator if we repeat the process 10,000 times. We already did a probabilistic analysis of the estimator. We saw that if we have a population with this population mean and this population variance, and we sample independently and uniformly at random from the population, then the mean of, well, I jumped the gun there, then the sample mean, which is a random variable, and this is very important to remember, we indicate it by putting a squiggly line on it. The sample mean of these measurements is going to have a mean that is equal to the population mean. What does this mean? I'm saying mean like 100 times a sentence, but what are the implications of this? This distribution that we just saw is centered at the actual population mean. Being centered at the actual population mean is not enough. We want the estimate to be close to the actual population mean. Well, we proved that the standard deviation of that distribution of sample means scales with 1 over square root of n times a constant that is equal to the population standard deviation. This is very important because as n grows, that means that the distribution becomes more concentrated around this population mean parameter that we're trying to estimate. I don't know if I said that, but that standard deviation is the standard error that we discussed in a previous video. So when we look at the distribution of the sample mean, here we're seeing it from a equals 20. As we increase n, the distribution indeed concentrates tighter and tighter around the population mean, which is our parameter of interest. We already established this when we derived the bias and the standard error of the sample mean estimator. Here is a picture where we see the sample means for different values of n, and indeed we see that eventually the distribution concentrates, and the way it concentrates is exactly following the expression of the standard error that we have derived in the previous video. This is an example of a wider phenomenon where if you have independent random variables with a fixed mean and finite variance, and you consider a sequence of them, so here we no longer have just little n random variables obtained, for example, via random sampling from a population. Here we assume that this sequence goes on and on and on, okay? Now what we're going to do is we're going to define the running mean of that sequence. So first we take the sample mean of just the first entry. Then we take the sample mean of the 2 first entries, then 3 first entries, and so on and so forth. Okay, we're going to denote, to make it very clear that there's a dependence on the number of entries that we are considering, we're going to denote this by m sub n. Okay, this is exactly the same as if we're taking random samples from a population. First we take 1, then we take 2, then we take 3, and so on and so forth. Well, it turns out that if we look at the mean of this running average, I'm going to say running average so I don't say mean 3 times in every sentence. We look at the mean of the running average by linearity of expectation. This is just equal to 1 over n and the sum of the means of the individual random variables, but they all have the same mean. So this is just equal to n times mu, so the mean of the running average is just mu. Here I have just reproduced our derivation of the bias of the sample mean when we take random samples, okay? Because again, this sequence of independent random variables can be interpreted as random samples from a population, but it doesn't have to be, it's a little bit broader. Okay, so what happens with the MSE between this estimate of the underlying mean and the actual mean? Well, now that we know that the distribution of this guy is centered exactly at the true mean, what is this? This is just the variance, by definition, right? It's the variance of this guy, which is equal to this running average. Now, this 1 over n can come out by the properties of the variance. It has to come out squared because the variance is a mean squared of the difference between the random variable of interest and its mean. And now, this variance, the variance of a sum when the random variables are independent, is equal to the sum of the variances. We established that in the video on the standard error. So we have that the MSE, the mean squared error between this running mean and the true mean of this distribution, actually is equal to 1 over n squared times the sum of the variances. But all the variances are equal to sigma squared. So here we obtain sigma squared divided by n. This is exactly the derivation that we used to derive the standard error of the sample mean obtained from random samples, because again, this situation can be thought of random samples obtained from a population. Okay, so now let's think in terms of convergence, because again, now we're not thinking of we just have n samples. This sequence goes on and on. So we can in particular consider the sequence of mean squared errors. Of course, at the beginning, they're not going to be great. We're using 1 sample, then 2 samples. But as we go on and on and on, the mean squared error scales as 1 over n, because here we're assuming that the variance is a constant. It's whatever variance the distribution of these guys has. Eventually, it converges to 0. So that means that the estimator, in a way, eventually is perfect. If we take the limit of the mean squared error of this sequence of running averages as n grows to infinity, eventually the error is 0. Now we're going to ask the crucial question that is going to take us to the law of large numbers. You say, okay, the mean squared error is 0, but what are the implications in terms of how much my estimator is going to deviate from the parameter that I'm interested in estimating by a certain amount? So let's say that you say, okay, here I'm interested in knowing what's the probability that I'm going to deviate by more than 10 to the minus 3, let's say, as n grows. Okay, so again, this is the mean of these random variables that you want to estimate. This is your running average, where you're taking more and more of these random variables that have the same mean and finite variance. And you're interested in saying, eventually, what is the probability, for n, I don't know, equals to 1000. What's the probability that I'm going to deviate by more than 10 to the minus 3? We can actually look at those probabilities in terms of a sequence, right? So you fix some epsilon, you fix 10 to the minus 3, or you want to be very strict, 10 to the minus 10, and you say, okay, the probability at the beginning is probably going to be very large because, you know, the estimator is not so good, but eventually what happens to this probability as n grows larger and larger and larger? What happens to the probability that I deviate by 10 to the minus 4 or 10 to the minus 10 from the estimator that I'm interested in? And that's the law of large numbers. In the law of large numbers, we're going to show that that probability is always vanishing no matter what epsilon we pick. We'll take a look at a picture of this to make things clear. But in order to do that, in order to be able to establish that result, we need to be able to bound probabilities using the mean and variance of a distribution. Why am I saying this? Because we know the mean and the variance of this distribution of running means as n grows, but that's not exactly what we're interested in. We're interested in the probability that the running average deviates by a certain amount. So we need to connect these two concepts through an inequality that we're going to call a deviation inequality. The simplest deviation inequality is Markov's inequality. Markov's inequality states that a non-negative random variable with a very small mean cannot take large values with high probability. Why? Because if it could take large values with high probability, that would drive its mean to be larger. Let's actually prove this. We're going to prove this in the discrete case. The proof for the continuous case is almost exactly the same. So we're going to have a random variable a that has a certain discrete range, and we're going to pick a certain constant c that is greater than 0. And now we're interested in bounding the probability that a is greater than c. Remember that a is non-negative. Okay, so I'm going to write it here because it's super important. Non-negative, and I should have, of course, now it will disappear when I continue with the slides, but I just want to emphasize it's very important that the discrete random variable is non-negative, because otherwise this doesn't make any sense. Okay, we want to bound the probability that it's larger than a certain constant using its mean. Okay, so let's write its mean. Its mean is just equal to every possible value that the random variable can take, weighted by the corresponding probability mass function, which is the probability that the random variable takes those values. Now we're going to separate the values between those that are smaller than c and greater or equal to c. Okay, and if you realize, because all of these quantities are non-negative, we can actually bound these guys by saying, well, all of these a's are greater or equal to c, so I can just plug in c there and I get a lower bound on that because they're all non-negative. Otherwise, this does not work. And now this quantity is lower bounded by just this because, again, that is non-negative. So we have this bound that we can kind of move around to bound the probability, because this is the probability that a is greater or equal to c. Okay, so that's the probability that a is greater or equal to c. By this bound, it's upper bounded by the mean divided by c. This establishes that if the mean is small, then a cannot be, the probability that a is greater than c cannot be very large. Again, if it were, then it would drive the mean upwards. Okay, and look at the dependence on c. The bound is smaller, the larger the constant c is, which makes a lot of sense. Again, for a non-negative random variable, here I did emphasize this adequately. There's this bound on the probability that a is greater than a certain constant, which is the mean of the random variable divided by c. All right, so let's take a look at an example. The mean age of, I'm making this up, okay? So this is not from, like data or anything, but so imagine that we have established that the mean age of NYU students is 20 years old. We want to bound the fraction of those students that are above 30. We can apply our bound where like the probability that this random variable which captures the age of NYU students, which obviously is non-negative, the probability that it's greater than 30 is bounded by the mean of the random variable, which is 20, divided by 30. So we're guaranteed that at most 2/3 of the students are above 30. There cannot be more, because if there were more, then that would drive the mean to be larger. Okay, as you can see, the bound is not super tight. We will get back to this point. Okay, so we're not super interested in random variables that are just non-negative. We're interested in random variables in general. I mean, this is what we will need to establish the law of large numbers. So it turns out that we can use Markov's inequality to prove a related inequality that is very useful for the analysis of statistical estimators. This is Chebyshev's inequality. It states that when a random variable has small variance, it cannot be far from its mean with high probability, which makes a lot of sense because what is the variance? The variance is the mean of the squared deviation of the random variable from its mean. So if that variance is really small, if that variance is really small, then the random variable cannot be far from the mean with high probability because that would make the variance larger. That is the intuition here. So okay, so let's prove this. We take a constant c, and we take a random variable a with bounded variance. We're interested in bounding the probability that the random variable deviates from its mean. This is the mean, by the way. The mean of a is mu, by a certain constant c. What are we going to do? Well, we're going to realize that what do we have here? Let me highlight this. What do we have here? The square of the random variable minus its mean is a non-negative quantity that is actually random because a is random. So we can say that this is a random variable b, and we can just apply Markov's inequality because this is a non-negative quantity, a non-negative random variable. So this is going to be smaller or equal to e of b divided by c, right? And now we can plug in a minus mu there. And that's exactly what we're going to do. This is bounded by the mean of the square root of a minus its mean, all of that divided by c. But what is this by definition? If the mean of a is mu, that's just the variance. So the probability that the square of the random variable deviates by c is bounded by the variance divided by that constant c. Let's take a little detour because this is going to allow us to establish a result that we needed when we were talking about correlation. And the question here is, what happens when a random variable has zero variance? It doesn't, the mean variation around its mean is actually zero. We can actually use Chebyshev's inequality to see what happens. So we have a random variable a with a certain mean mu and a variance zero. Then what happens is that if we consider the probability that the random variable deviates by any epsilon from the mean, that's bounded by the variance divided by epsilon squared. Remember that when we proved Chebyshev's inequality, we had squares on both sides. That's in case you're wondering where does this square come from. But now the variance is zero, so the probability of any deviation is zero. That implies that if the variance is zero, then the probability that a random variable is equal to its mean is equal to 1. And specifically, if the mean squared is zero, which implies that the variance is zero, but also the mean is zero, because the variance is equal to the mean square minus the square of the mean, then that random variable is equal to 0 with probability 1. And remember that we needed this for our analogy of random variables as vectors in a certain vector space, and in particular to prove that the covariance was a valid inner product. And also in our proof that when the correlation coefficient is equal to 1 or minus 1, then two random variables are completely linearly related. Okay, so now we have a formal proof for that. Okay, let's go back. So we have the Chebyshev's inequality. Let's take a look at this example for the age of students to show that when you take into account standard deviations, you can usually obtain much tighter bounds on probabilities. So here we want to bound the fraction of students above 30, and we realize that the standard deviation is actually only 3. So in order to use that information, we're going to apply Chebyshev's inequality. The probability that the students are above 30 is smaller than the probability that they are above 30 or below 10. Maybe we have some geniuses that are 9-year-olds running around here. That's the probability that A deviates from its mean by more than 10. Here we can apply Chebyshev's inequality. Remember that when we established it, we had squares here and here. So this is going to be bounded by the variance divided by the square of 10 divided by 100. The variance is 3. So No, the variance is 9 because the standard deviation is 3. I have this trouble with squares, okay? So 9 divided by 100 is just 0.09. We get a much tighter bound on the possible number of students than with Markov's inequality. Of course, this is not fair for Markov's inequality because here we have this important information that the standard deviation is actually equal to 3, which constrains the problem further. Okay, but this just shows you how to incorporate information about the standard deviation to get tighter probability bounds using Chebyshev's inequality. Okay, so now armed with Chebyshev's inequality, we're going to go back to our problem of interest where we have this sequence of independent random variables that have mean mu and variance sigma squared, which again can represent random samples from a population. So we had this running average, which we're interested in controlling. And now we're going to take a look at the probability that the running average deviates from the mean by a certain constant. So you have to think of this epsilon as something very small, I don't know, 10 to the minus 3, for example. This is bounded by Chebyshev's inequality, by the variance of the running average divided by epsilon squared. What is the variance of the running average? It's sigma squared divided by n, okay? We're going to, for some reason, I decided to repeat the derivation here. It's, you know, it never hurts. So we plug in the value of the running average. This guy is going to come out squared, and we're going to end up with the variance of a sum of independent random variables. That's just the sum of the variance, and that variance is equal to sigma squared. There's n of them, so the n's cancel out, but here we had n squared. That's the crucial part that is given to us by independence. So we end up with this expression. Realize that epsilon is very small, okay? So this bound is going to be very large if we fix n. But as n goes to infinity, eventually it's going to go to 0, no matter how small epsilon is. And that is the law of large numbers. For any epsilon greater than 0, no matter how small epsilon is, when we push n towards infinity, this is going to converge to 0. The probability that the running average deviates from the true mean by more than epsilon is eventually going to converge to 0, no matter how small epsilon is. That's the law of large numbers. We're going to now look at the implications of the law of large numbers for statistics. When we have random measurements obtained through random sampling from a population, and we have a deterministic parameter gamma that we want to estimate from those random measurements, we say that the estimator is consistent if for any epsilon, the probability that the estimator deviates from the parameter of interest by more than epsilon is equal to 0. So you can see that if we plug in the sample mean, this running average here, and the mean here, this is exactly what we got with the law of large numbers. So the law of large numbers immediately tells us that the sample mean is a consistent estimator of the population mean. Let's make sure that we make this point very clearly. If we have a population with big N points and a population mean that has this population mean and this population variance, then we already established that if we take random independent samples from the population, the mean is always, as long as the samples are independent and uniform, taken uniformly at random from the whole population, then the mean of each sample is always the population mean, and the variance of each sample is always the population variance. So we do have a sequence of random variables that have a certain mean and bounded variance equal to, in this case, the population variance. So we can directly apply the law of large numbers to show that the sample mean converges to this guy, to the population mean that we want to estimate in probability. For any epsilon, and let me show you a picture, for any epsilon here, so this would be, this is 2 epsilon, but anyways, this is plus and minus epsilon, as you can see here, from the population mean. Eventually, when we look at the sample means, they're all going to be concentrated between mu, the population mean plus epsilon and the population mean minus epsilon. This is for the height data that we had seen earlier. This makes a lot of sense because due to how the standard error decreases, we expect the distribution to be very concentrated, but now we have a formal proof that eventually the probability that we have a deviation of epsilon from the mean for any epsilon eventually is going to be 0. So eventually all the samples are going to be restricted to be between the parameter of interest, the population mean plus epsilon, and the parameter of interest minus epsilon. And this is the implication of the law of large numbers for the estimation of the population mean from random samples. Okay, hopefully this allows you to visualize it. All right, so what have we learned? We have learned to control probabilities using the deviation inequalities, so Markov's inequality and Chebyshev's inequality. We have established the law of large numbers that says that a sequence of running averages eventually will converge to a mean as long as the underlying random variables are independent, have the same mean, and have bounded variance. And we have seen the consequence for statistics and data science, and that is the consistency of the sample mean. Eventually, if we take enough random samples, the probability that our estimator deviates from the true population mean by any epsilon is going to be 0. Usually I would say that's all I got, but I want to give you a little bit of a motivation about why this is not the end of the story. So here we have used this bound to show that eventually, our estimate of the population mean converges to 0, which is the sample mean minus of n samples minus the population mean. The probability that deviates by epsilon is bounded by the variance divided by n and by epsilon squared. But now I can go and look at my experiment where I have these heights and I can evaluate these quantities. This guy I can evaluate immediately. Okay, I can set epsilon to be 1 centimeter or less if I want to, and I can estimate this quantity for any n. Very easy. This quantity, how would you estimate it? Maybe think about it for a moment. Well, you can use Monte Carlo simulations, right? You can take this number of samples over and over again and just take a look at how many times, let me erase here, how many times this guy is greater than that epsilon that we had fixed. Okay, that fraction, like over the number of your Monte Carlo simulations, is going to give you an estimate of this probability. So we're going to do exactly that for our height data in order to see how good this bound is. Is this bound very tight? If we want to actually estimate this, does it make sense to try to estimate it using this expression? And what we observe is that the bound is not tight at all. Okay, so these are the actual values that we estimate with Monte Carlo simulations. And what we see is that indeed we have an upper bound. We have proof that this is an upper bound, so this is always nice to see that proofs actually hold numerically. But the upper bound becomes extremely loose as n grows. So this does not really characterize the probabilistic behavior of the tails of the distribution of the sample mean. It does not. It just tells us that eventually the tails go to 0. Okay? If you want to actually characterize the distribution of the sample mean as n grows large, you have to use an even more powerful tool from probability theory, which is the central limit theorem. Okay, so here we see the line here is the approximation of this probability given by the central limit theorem, and as you can see, it's pretty awesome. We're going to talk much more about that in following videos. And now that's all I got. Thank you very much.